So what is the learning outcome of this particular lecture? After the completion of this lecture, student will be able to justify the necessity of transistor sizing. What is meant by transistor sizing? I already taken that in the last point, that comparison I have taken, pull up and pull down. So there I told you transistor sizing is required, means you need to increase the length of or W by L ratio of PMOS transistor. Okay, that we will take it again over here. And second is the find the W by L ratio of PMOS and NMOS according to the rules of transistor sizing. So this is again a very important topic, because there are so many lectures or top points material is available, but it is somewhat confusing. So before reading that thing, if that is cleared over here, some part is cleared over here, so you'll be able to understand it in easy way. So what is the requirement of transistor sizing? First thing, why we need to go for transistor sizing? Will it not be proper if I'm not doing the transistor sizing? So what is the reason? As I told you, whenever there is a capacitor connected to load, this is the inverter I'm saying, this is the PMOS and this is the NMOS, suppose. And when the PMOS is on, this is acting as a resistor, and when NMOS is off, it is acting as an open switch, as I told you earlier also. And one capacitive load is connected over here, because for any circuitry, definitely load is there. So here we have considered the capacitive load. Now, suppose I have given logic 0. What will happen? Here, I'm just highlighting this. If I have given logic 0 at the input of these devices, what will happen? This PMOS will be turned on and it is acting as a closed switch having certain resistance, minimum resistance, on resistance. So denoted by this RP, resistance of on resistance of PMOS. And this will be in the off state. So this is the open circuit. So current will flow from what? VDD to this output. So capacitor will charge up to VDD. Now initially, what is the voltage across capacitor? That is 0. So it will charge from 0 to what? VDD. Why VDD? Because PMOS passes strong 1, and that's why here that is written 4.5. But if the voltage VDD is 4.5, it will charge up to 4.5. If VDD is 5 volt, it will charge up to 5 volt. There will not be any losses over here. So this is called as TPLH. What is TPLH? Low to high, means capacitor is charging from low to high. So TPLH, that is the time. Now, when I am giving logic 1, what will happen? This will be off and this will be on, and capacitor will try to discharge. So what will be the case over here? Now, previously capacitor is having the voltage, that is the maximum voltage, logic 1. Now it will try to discharge. So it will be TPHL, high to low. That is the time known as TPLH. What is time which is going from high to low? So low to high is related to what? PMOS, because PMOS is on, so capacitor is charging. So capacitor is charging from low voltage to high voltage. But whenever the NMOS is on, capacitor tries to discharge. So that's why that time period is called as a TPHL, high to low. So don't get confused over here. So charging and discharging. So what is the role of transistor sizing? You are able to see here diagram, that is green, red. So here this is the particular concept of microwave. You need to draw the transistor in this way. So this red indicates polysilicon, which is forming a gate of the transistor, and this W is the this parrot color you are able to see. This is the diffusion, and plus P plus diffusion we are having, because doping forms your N region or P regions in the transistor. So this is the doped region. So here it is a source, this is the drain, okay, and this is the gate. So these are the 3 terminals available. Now what you need to do to have same charging and discharging time, I told you in the earlier lecture also, those who are absent, I'm just trying to draw this. So capacitor is charged from 0 to VCC and discharged from VCC to ground. If this charging point, this is what is the charging time, okay, and this is the discharging time. So charging time over here is this much and discharging time is what? This much. So suppose whatever I had drawn, but consider over here that both are same. So when charging is same as a discharging time, so on and off time is same, and that time it will act as a perfect inverter, and that is our requirement. Okay, so to have the same charging and discharging time, that capacitor should charge with the same time and discharge with the same time. The resistance should be same. Resistance should be same means current should be flowing through the devices should be same. And for that reason, what we need to do, we need to size the transistor. Now, what is the reason for that? So as I told you, there is a PMOS device as well as NMOS device present in the CMOS circuitry. And in NMOS, majority charge carriers are what? Electrons. And in PMOS, majority charge carriers are holes. Now, as you know, electrons are more mobile than the holes. So if the region of NMOS is this much and there are n number of electrons present over here, n number of what? Electrons are there. So current will be flowing, some current is flowing, but same amount of device space is there, area is there, which is of PMOS, and there are n number of holes present inside that. Still current flowing through this device is somewhat less than this device. Why? Because of mobility of electrons more as compared to the mobility of hole. And to match up this thing, that is for in both the transistors there should be same current. So what I need to do, I need to increase the W by L ratio of this PMOS. By how much time? That is 2.5 or 3 times. In the different book they have written differently, but just remember 2.5 times to 3 times your W by L ratio of PMOS should be more than the NMOS. Okay, so this I have taken in the last lecture also in detail. So just I have recalled this particular concept. So hope the things are clear. So why we require transistor sizing? Here it is shown as a double. I have told you 2.5 times, 3 times. Some in books it is taken as a double. So 2 times. So transistor sizing is necessary. Why we require transistor sizing? Because it is required to equalize the response time of charging and discharging of the load capacitor through pull down and pull up network. So to equalize the charging and discharging time. It involves increasing the width of MOSFET to increase the speed. Which MOSFET? You need to increase the width of P MOSFET, because N MOSFET is already having electrons which are the mobile charge carrier, or mobility of electrons is more. So I need to introduce same current in the PMOS. So I need to increase the width of the PMOS. So it involves increasing the width of here specifically PMOS to increase the speed. The response type of pull up network, that is PMOS. What is response time? This is PMOS where capacitor is charging from 0 to VDD. So TPLH. So response time of PMOS is denoted by TPLH, which is the time low to high, and pull down networks NMOS is called as a TPHL, high to low. So this is clear. And on this there is the question. There are the questions for the poll. So hope this particular point is clear. Okay. Next. Now this is again very important. These 2 slides are very important because this is the actually logic. Now you know that in pull up PMOS is connected and in pull down NMOS is connected. Intersection of this there is a formation of output, and inputs are connected together to form a common input VDD to the pull up and VSS, that is ground, to the pull down. That is clear to you. Now I'm just reading this thing. Just try to understand this thing very effectively and be attentive. For silicon material, because silicon material is used for manufacturing the devices, the electron mobility is about 2.5 to 3 times greater than the mobility of hole. So in here you are having holes, but here you are having electrons. So mobility of electron is more as compared to the mobility of hole. Therefore, to have equal rise and fall time, why you require transistor sizing? To equalize the charging of capacitor, charging and discharging of the capacitor. So to have equal rise and fall time, what you need to do? We must choose W by L ratio of PMOS as 2.5 times greater than the NMOS. So I need to increase the W by L ratio of this PMOS. If W by L ratio of this NMOS is 1, so PMOS will be 2.5 times of that N, means it will be 2.5. Okay. So after performing this task, we need to size the transistor of each gate under worst case condition. Now what is meant by worst case condition? I will be telling you in the coming PPT, next PPT. Of the input combination. For charging and discharging, resistance are, suppose I want to write certain notation for the charging of capacitor and its resistance. So here it will be charging. Capacitor is charged through PMOS. So RC I am writing charging resistance, and capacitor is discharging to this NMOS. So I will be writing RD, that is the discharging resistance. So every gate circuit, the pull-up network provides maximum on resistance. This is on resistance because capacitor will be charging, and pull-down network provide maximum on resistance for fall time. That is rise time. This is the maximum on resistance, and for fall time, this is the maximum on resistance. So that is related to NMOS, and this is related to PMOS. So hope these things are clear. The main thing is in the next PPT. So this is what is the main thing. Electrons mobility is 2.3 or 3 times greater than the PMOS. So you need to size the transistor. Now, what is this worst case condition? I am concentrating on this particular point. Now, this diagram you are able to see. What type of diagram this is? I told you how to find out the equation. See what is the NMOS devices are connected. So here, how many NMOS devices are connected? So here there are 2 NMOS devices are connected. That is A and B variable related to this variable. Series means NMOS are in multiplication. So series means A into B. So I am writing A into B, and CMOS logic implement inverted logic. So A into B complement, whole complement. So this is nothing but what? NAND gate. Okay, so this is clear. Now here NAND gate, 2 PMOS are in parallel and 2 NMOS are in series. So here for the NAND gate, the worst case charging corresponds to. Now what is meant by worst case? Means how many transistor you need to turn on for charging and discharging of capacitor. Now here just think, at the time, because there are 2 paths available, that is from transistor 2 you can connect VDD to output, and through transistor T1 you can connect your output to the VDD. Okay, so my first this is what first path is what this. Okay, and second part is what like this. So I am having 2 paths. So either this or this, my current will flow, and I will be having path for charging the capacitor. So worst case condition means I want only one transistor to be on. So here I require only one transistor to be on for charging the capacitor or connecting this VDD to the ground. But now consider these things. These 2 transistor NMOS are in series. Now to connect this ground to the output, what I require? I require both transistors should be on. If one of the transistor is on and one is off, I will not be getting the path for transistor this output to discharge or capacitor to discharge. So here what is my worst case condition? I require 2 transistors, that is both the transistors should be on. If one of the transistor is off, then I am not able to get my path for discharging the capacitor. So what is my worst case condition over here? Hope you you're understanding. Here I require only one transistor to be on for capacitor to be charged, but I require here, as these are in series, I require 2 transistors to be on for capacitor to discharge. And that's why here it is written, this is related to what? Capacitor charging. So resistance of charging capacitor and resistance for discharging. So RD. So what you need to do, right? So RC by RD is what? RC is what? 1. So it is written 1, and RD is what? 2. So 1 by 2 is written. So hope these things are clear. Worst case scenario means for charging or discharging of capacitor, at the most, how many transistors should be on for getting full path? Okay. So here that condition is that 1 by 2. Now, what we learned before to this, that as the mobility of holes are less as compared to the mobility of electron, I need to double or 2.5 times or whatever the written in the book. Here we are considering 2.5 times, it should be more. So that's why I need to increase the W by L ratio of this PMOS. By how much? 2.5 times, because mobility of electrons are 2.5 times greater than the hole. And that's why here it is written that W by L of P is equal to 2.5 times of N. So what is N over here? That is 2. So 2.5 times of N. Now, if I am considering Wn, that is W by L ratio, where we have considered L is kept constant and to avoid the complication. So we are just changing width and comparing width of PMOS and NMOS. So suppose width of NMOS is 180 nanometer. What is this 180 nanometer? That is the length. Whatever you are able to see this particular structure, and this is what is the doping. Okay, this is suppose the N plus doping. So this is region is the length, and the size of this channel is what? is denoted by this technology, 180 nanometer technology. So now this length is what? 180 nanometer, and this is for what? WN, width of N MOSFET. Okay, now what should be the width of P MOSFET? 2.5 times that of the N MOSFET. So here you have already considered for the worst case scenario, that is 1/2. So it has been taken 2.5 into this is WN, 2 times W by L of N. Now as it is 180 nanometer, so what will be the P? That is 2.5 into 2, that is 5 times of this. And here it is written in the nanometer, but here it is written in the micrometer. You can change the this units. So 18 fives are 90, and that is the 5 times you have taken this more. 5 times why? Because 2.5 into this, what is the worst case scenario you have considered, and that's why it is term is coming as a 5. Actually it is 2.5 time only, but because of this 2 already it's present over here, it is 5 times. So 18 fives are 90. In this way you are getting this particular WP of the PMOS. So this is called as the transistor sizing. If you are taking same W by L as of that N, what will happen? Charging and discharging of this capacitor will be having different timing, and that's why you are not getting proper on and off time. So for having same charging and to equalize charging and discharging of capacitor, what we need to do? We need to do the transistor sizing. And transistor sizing is related to what? Changing the W by L ratio of what? P MOSFET. Hope these things are clear. If not, okay. So before going to that, just I am going for the poll questions. So be ready for the poll question. Transistor sizing is necessary to equalize the response time of charging and discharging of load capacitor. So why we need to size the transistor? Because I told you I want capacitor to be charged and discharged at the same time. So I'm closing this poll within 5 seconds. 3, 4, 5. So 81% voted. So 95% voted for true and 5% false. So those who have voted false, because true is the right answer. To equalize capacitor charging and discharging, we need to do the transistor sizing. So just think on that and hope your idea is clear now. So I am just launching second poll question. So I'm stopping this poll. So what is the right answer? Capacitor charges. So charges means from low to high, 0 to VDD. So I can say TPLH. This is the right answer. Moving towards the next point. Now this thing, I'm not going in detail of this. Just go through this. Just I want to tell you, if the two transistors are in series or two transistors are in parallel, what will be the equivalent resistance? Okay, because this point is required to understand the transistor sizing. Okay, but I'm not going in detail. Just remember that equivalent resistor for series connected transistor is R1 plus R2. As you know, rho L by A, where L is what? Your L by A length and width. So area is what? Width into thickness. So this is T is what? For the thickness, and it is directly proportional to 1 upon W by L. Now whenever you need to find out series connection, so this will be explained in this way. So my series equivalence of true transistor or n number of transistor will be like this. Okay, now just for the information, just add, because this particular point will be used in the coming PPT for finding out the transistor sizing. So if I am having two transistors in series, so I have written here W by, according to this equation. So W by L equivalent of this two transistor connected in series is 1 upon L by W, because here it is changing. Over here it is changing W by L to L by W. Okay, so don't get confused over here why that L by W is coming. So I have written like this, and if the two transistors are of same size, so I can just remove this 1 and 2. So this is the condition. So this equation is very important. That is W by L equivalent for the two transistor is equal to 1 upon 2L by W. Okay, and when two transistors are in parallel, it is equivalent is written as 1 upon R1 plus 1 upon R2, and its equation is will be like this. So most probably we are using this equation only, and why that we will see in the coming PPT. So just remember this particular equation. Rest of the thing just read in the from the notes. Okay, so now PMOS dimension. Now you need to find out the transistor sizing, and where PMOS dimension is given as the W by L ratio, which is 3, and for NMOS it is written as a W by L equal to 2. Now you need to remember this equation. Okay, so I'm just switching this from this to this. Okay, so this is the diagram I have taken, and on the diagram there is nothing is written. This 6 by 1, this is because of transistor sizing I have written. Now how this comes? Okay, so what you need to do, hope this is visible. So what you need to do, the steps you need to follow. First, whenever the equation is given, suppose this equation is given, you need to draw this diagram. That is the first step. Okay, so that already we have seen in the previous PPTs or lecture. So now what you need to do? Now in the problem statement, it has been given that PMOS is having the 3 by 1 of W by L ratio, and for NMOS it is having 2 by 1 of W by L ratio. Okay, 3 by 1 means nothing but a 3, and 2 by 1 means nothing but a 2. Just for the sake of W by L, it is written in that way. Okay, now here I told you this equation. Okay, this is for the series transistor, when two transistors are in series. Now as I told you in the transistor sizing of NAND gate, worst case scenario. What is worst case scenario? Means VDD, how VDD is connected to this output, means how many transistors in the worst case should be on, and for all the cases there should be same charging and discharging time that we want. Now here just see, I have just already done this particular thing, so I'm just switching. Here what is the thing in this PMOS, what are the options available for VDD to connect to this output? So that options are, just follow that blue line. This is first option, means if only A is on, that can pass through the A, current will flow from A, or capacitor will get path from A. Next, second is path is what? That is C and B. This is the second path available. Hope you are understanding thing. And third, that is the last, from which D and B, the capacitor will be getting charge path. So now in worst case, what is happening? Both two transistors should be on. First, only one transistor is required to turn on, but in second case, for the green case, you require C and B to be on, and in third case you require D and B to be on. Okay, now what is the thing? If the transistor this A is on, so capacitor will charge through this particular path, and here the resistance will be somewhat related to 3 by 1. But now instead of this, only these transistors are on, so there should not be any change in the resistance, because I told you why we are doing the transistor sizing. We are doing transistor sizing for having equalized on and off time, that is the charging and discharging time. So it is now 3:53. I just want to wind up. I will repeat this thing again in the next lecture, but I just want to complete this part over here. So here, if I am writing 3 by 1 over here for this transistor and 3 by 1 over here, so my overall resistance will be different. But I want my resistance, that is charging time of capacitor, should be same from this path also, from this path also, from this path also. So I need to manipulate the W by L ratio. So how to do? So I have told you there are three paths, that is blue, green, and orange. Now what you need to do? As you know, this is the equation. So here I want W by L ratio to be 3 by 1 for this case also and this case also. So I need to find out equivalent W by L ratio for C as well as B. So how to find it? That you know this equation, W by L, hope this is visible. W by L equivalent is equal to 1 upon 2 L by W. Now what equivalent is given? That is given as a 3 by 1. So I have written 3 by 1 over here. And what is this? 1 upon 2L by W. So I have written 2L by W. Why? Because there are two transistors coming in series. And that's why if I'm solving this, my W by L ratio comes as a 6 by 1. So here I need to write 6 by 1 and 6 by 1. So whenever this 6 by 1 in series, it actually gives 3 by 1. That way it is just justified. Again, same time, when I want this to be path to be selected, again there are two transistors. So what should be my transistor W by L ratio for respect to transistor? It will be same, that is 6 by 1, because there are two transistors coming in series. And that's why here 6 by 1, 6 by 1, 6 by 1 written. Why? Because if capacitor is getting path from this, it will be getting 3 by 1. Again, if capacitor is getting path from this particular green arrow, again equivalent resistance, that should be 6 by 1, 6 by 1 equivalent will be 3 by 1 only, and at this path also that should be 3 by 1. So in any case, worst case scenario, in any of the option the path is getting, so capacitor will be taking same time to charge, and that's why we require transistor sizing. Okay, so Next, I'm just quickly telling about this one. So here 2 by 1 is the transistor sizing, but if I'm writing 2 by 1, 2 by 1, 2 by 1, 2 by 1 over here, I will be getting some different charging and discharging path for the transistor or capacitor. So what you need to do, you need to again size the transistor. So first option is not available. The output is connected to the ground through this first red path. So this is the path available, that is A and B, and second path is available, that is A, C and D. So in A, C and D there are 3 transistors available, and A, B there are 2 transistors available. So again this equation you are having. So what you need to do here, as I am having 2 transistors over here and W by L is of 2 by 1. So here it is mentioned, and that's why my equivalent W by L for this 2 transistor coming in series is what? 4 by 1, and that's why it is written 4 by 1, 4 by 1. Now, in next case, what are the transistors coming? There are 3 transistors coming, that is A, C, D. But this resistor transistor sizing should be equal to this series transistor. So what is the transistor sizing? That is equivalent is 4 by 1. So I need to match that with this. So how I am getting 4 by 1? So here there are how many transistors? 1, 2, 3. But here there are only 2 transistors. So what you need to do? My equivalent transistor sizing is 4 by 1. So here I have written 4 by 1. This equation I have solved, so I'm getting W by L of 8 by 1. So that way you are getting this. This is just for your understanding I had told you, but there is another simple way available that I will be taking in the next class. So before joining the next class, please clear this concept of transistor sizing. That is how I have written 3 by 1, 2 by 1, 4 by 1. Simple way of this without this calculation I will be telling you in the next lecture. Hope this you have understood.